Okay, hello everybody. Welcome to the third session on transport. My name is Dražen Verhovski. I will be your host today. I do believe that from the previous sessions and from the information available on who are you have more or less got a feel who I am and where I come from. So just briefly, I am a transport consultant from Croatia, based in Croatia. And clearly in my spare time, I also run sessions like this. However, given that this is my first session, I guess I'm not very good at that. So unless I turn out to be a rubbish host, I think that eceee will definitely have to invite me again next year to help me develop. Right, today we have interesting presentations and interesting speakers, but before that, I would just also use the opportunity to introduce my co-host today. This is Neil Wallis from the Zemo Partnership, and now I will ask Neil to say a few words about himself. Neil, would you please?
Hi, Dražen. You're going to be a great host. Don't worry. I'm here from near Oxford in the UK. We've got a lovely Mediterranean week here, a bit like the south of France. But I actually work for an organisation called eceee. One of my clients is the Zemo Partnership, which used to be the Low Carbon Vehicle Partnership, which some of you may have heard of. Also, I'm sure you will have heard of the Energy Saving Trust, a former employer, and I've also worked for the Renewable Energy Association in the UK as well. But now I sort of spread my work more widely. But I look forward to hearing from all of you and look forward to the discussions afterwards.
Okay, thank you, Neil. So our first speaker and our first presentation today is going to be done by Thorsten Clemens. Thorsten is a chief scientist for reservoir engineering in OMV. He has been working in Shell and OMV on various aspects of improving the recovery efficiency from hydrocarbon fields. And he has also worked on CO2 geological storage, zero emission power plants and fuel cells. Currently, he's looking more into energy transition. And today he will be talking about, as far as I'm concerned, a very interesting subject. And he will present a paper which has research which has been comparing battery electric vehicles with plug-in hybrid electric vehicles and ICE vehicles and their contribution to decarbonization of private transport. So, Thorsten, the mic is yours.
Hello, my name is Thorsten Clemens and I'm working for OMV EMP. First of all, I would like to acknowledge my co-authors Marcel Clemens from the University of Applied Science in Wales and Markus Zechner from Stanford University. The title of the presentation is Electric Vehicles, Internal Combustion Engine Vehicles, and the role of hydrocarbon storage and carbon capture and storage for decarbonization of private transport. So in the last couple of years, we saw a strong increase in the electrical car stock, up to now more than 7 million units. Most of these cars are battery electric vehicles, BEV, about 60%, and 40% are PHEVs. So what is the reason for having this strong increase in electrical vehicles? One of the reasons is the aim to reduce greenhouse gas emissions from private transport. But what are we actually doing when we are shifting away from internal combustion engines to electric vehicles? So there are two types of CO2 sources. There are distributed sources, for example, public transport or private transport, which is on the left side. So these sources are usually along roads and cities, and they are very difficult to capture and to reduce. And there are point sources like industrial sources or sources from energy generation. And for these sources, we could have carbon capture and storage, for example. So what we are actually doing by having electric vehicles is shifting the distributed sources from the left to point sources on the right, which we will see in a moment in this presentation. Here we compared 3 types of car users: small, medium and SUV car users. And we were looking into 3 different types of countries: coal-dependent countries with high CO2 emissions of more than 700 grams CO2 per kilowatt hour, gas-dependent countries with 400 grams CO2 and per kilowatt hour, and hydropower dependent countries. So first we can compare the CO2 emissions from electrical cars with a certain electricity consumption in kilowatt hours per 100 kilometers to petrol cars with liters per 100 kilometers. So if we take an electrical car with a consumption of 20 kilowatt hours per 100 kilometers on the y-axis, then we see this is equivalent to about 1 liter per 100 kilometer of a petrol car in a hydropower dependent country. For a gas dependent country, this increases to about 3, and for a coal dependent country, above 5 liter per equivalent per 100 kilometers. What it means is if we are located in a coal dependent country and we are driving an electrical car which has a consumption of 20 kilowatt hours per 100 kilometers, it at least will emit as much as 5 liters as a conventional car with 5 liters per 100 kilometers. So this is the bare minimum it emits. In addition to that, we have the emissions from the battery construction. So here we are comparing CO2 emissions, incremental emissions, so we are neglecting the emissions related to car manufacturing, as a couple of authors already showed that these are relatively equal for ICEs and EVs. So on the left side we see the impact of different car types for gas-dependent countries. So we start off with a legacy or an initial emission at year 0 because of the emissions related to battery construction. And then the slopes of the emissions depends on the car type and on the country type. So here in the gas-dependent country, just on the left side, the figure A, we see that emissions from a SUV can amount up to 30 tons per in the lifetime or in 10 years, even for a battery electric vehicle. On the right side we see the impact of different electricity mixes, so here for a small car, while emissions related to hydro power are small compared to other cases. Coal-dependent countries can have substantial emissions even for small cars. For plug-in hybrid electric vehicles, there's one additional factor which we have to consider, and that's the electricity utility factor. And first on this diagrams on the left side we see the cumulative percentage of kilometers traveled versus driving distance. We see this type of diagrams more often with the amount of trips per versus as percentage versus driving distance, and there the curve is increasing much steeper, which means that only a very small percentage of trips is above 100 kilometers, and this is an important factor for battery electric vehicles because it gives us a feeling for how often we would need to change to other means of transportation or have to reload the car when we are traveling. For PHEVs, the cumulative percentage of kilometers traveled is important, because here it says 50% of the trips have a cumulative driving distance of larger than 35 kilometers. Because we take into account that the fewer trips have, but they with longer distances, but that the distances are longer. And this can be used in addition to the driving patterns per day to come up with a utility factor, which means how many kilometers are we traveling electrically versus how many kilometers are we traveling with fuel. And as you see in this diagram, we start with a lower initial CO2 emission burden, because the batteries are usually smaller for the PHEVs. And then the slope of the increment here for a gas country is steeper the lower, the more we drive with petrol. And 0% means we just drive with petrol, and then of course the slope is related to the CO2 emissions related to the fuel consumption. The yellow one would be purely electrical consumption, and anything in between is related to the utility factor. So if we travel 50% electrically, it's the middle blue line, which is a good value for private cars, but there are studies about that. So now when we compare the CO2 emissions of SOVs in this case, here we see on the left side for a hydropower dependent country, the ICE emissions, the orange dot would be 30 tons of CO2, lifetime CO2 emissions. BEVs have significantly lower CO2 emissions, and PHEVs, for them it depends strongly on the utility factor. So for a 50% utility, the CO2 emissions would be above the BEVs. The blue bars show the break-even time in years, and here, because of these initial CO2 emissions related to the battery construction, the break-even times for BEVs is somewhat longer for the PHEVs. We also see that the break-even times, as well as the CO2 emissions, of course, increase for larger battery sizes. For coal-dependent countries, the situation changes. So in particular for larger size batteries, in BEV cars, we have higher CO2 emissions for a lifetime or 150,000 kilometers compared to a ICE. Could have that. For PHEVs, they might be better off, in particular for higher electrical utilities. And the break-even times are significantly increasing for BEVs for coal-dependent countries. Let's have a look at the sensitivity. So in a hydropower-dependent country, for BEVs, the strongest, highest sensitivity is related to battery production emissions. And we have less emissions with the dependency on sensitivity with the electricity mix or electricity consumption. The reason is, of course, because the energy mix is already so good. With coal-dependent countries, we see that the lifetime emissions are significantly increasing compared to hydropower, and also the sensitivity increases. Here, the key parameter would be the electricity mix. So first of all, the electricity mix would be a good target to decrease the CO2 emissions from the electricity mix. For PHEVs, in both cases, the highest sensitivity is for hydropower, and coal and gas would be dependent countries in between, is fuel consumption. For hydropower, because the electricity mix is already so good, the sensitivity is not that strong for battery production, electricity and consumption and mix. For coal, the sensitivity of electricity consumption is almost as high as the sensitivity for fuel consumption. So it changed significantly from the hydropower dependent country. So if we look at the generation of electricity, then there should be a big drive towards renewable energy, and there are of course different sources for renewable energy. Here is a case for solar energy in Austria. So we see on the left-hand side that most of the solar energy is generated at roughly 12 o'clock, with a decline at in the morning or in the afternoon. This pattern fits reasonably well to the percentage of cars traveling. So we see that at midday there are less cars on the road, so they would be there for charging. But there will still be a mismatch because most of the cars will be, of course, available later and will be charged later in the afternoon. If we look at the difference between summer and winter, then there is a significant difference in the electricity generation. So this electricity generation, this difference, we have to store this difference in electricity generation. Wind energy is also not very stable, and the energy has to be stored. How can we store energy? We could use pumped hydro, we could use compressed air energy storage, or hydrogen. For larger amounts, as we might talk for deep decarbonization of public transport and private transport, hydrogen might be the method of choice. So we could store it in reservoirs and produce it back. Another option is to decrease the CO2 intensity by CO2 geological storage. In view of time, I didn't capture that here. And that is in particular important for coal-dependent countries. So, as conclusions, EVs, when we use EVs, this results in transferring distributed CO2 emissions to point sources. In most cases, EVs are leading to a CO2 emission reduction compared to ICEs. For hydropower-dependent countries, there are substantial CO2 emission reduction can be achieved. Highest sensitivity are battery-related CO2 emissions, so these have to be tackled first. Gas-dependent countries, about 30% CO2 emission reduction for our cases are achievable using EVs. Highest sensitivity has the electricity mix and fuel consumption for the PHEVs. For coal-dependent countries, the emission reduction for BEVs is limited, and in the worst case, the CO2 emissions might even increase for BEVs, in particular when they have large batteries. And PHEVs might reduce emissions. Highest sensitivity is electricity mix and fuel consumption. What we would need to judge the amount of CO2 emitted would be, in addition to the worldwide harmonized light vehicle test procedure, the fuel consumption of a PHEV driven with petrol only, and electricity consumption of the PHEV driven electrically only. In addition, the CO2 intensity of the energy mix in the respective country should be given. CO2 geological storage can be used to decarbonize electricity mix, and this works in particular for coal-dependent countries, because in coal-fired power plants we have higher CO2 concentrations in the exhaust gases, which can be more easy captured and stored. Hydrogen storage can be a very effective way of decarbonizing private transport and the energy mix. With this, I would like to thank OMV EMP for the permission to publish the paper, and I'm looking forward to receiving questions. Thanks.
Thank you, Torsten. Very interesting presentation, and I happen to be a fan of e-mobility. So, and every so often, I believe everybody bumps into an argument whether or not battery electric vehicles are really contributing the whole thing of CO2 emission reduction. And I'm glad that your research has shown that this has been the case, especially in coal independent countries. However, I don't see that we have, Neil, any questions on Hoover. Yeah, maybe one. Yeah. So one question from Habza Abid. As compared to ICE vehicles, do you take into account the reduction of components in the battery electric vehicles?
No, we neglected this part. So I've read a couple of articles where the difference was not that big, but this is something which should be taken into consideration. But I guess it's a more second order effect.
Okay.
Another question for Torsten Dragan, if that's okay.
Yeah, feel free. Yeah.
I think one thing that your paper pointed to, Torsten, was the importance of the embedded emissions in the production of electric vehicles compared with the whole life cycle. There's a big difference between, and we're in this phase now where we're deciding, what companies should market. Is it going to be an 80 kilowatt long range vehicle, or is it a 40 kilowatt vehicle that actually for most journeys is quite sufficient? I suppose, perhaps you'd comment on the significance of that dilemma that we face now, whether it points to sort of policy interventions to encourage people to go for vehicles with smaller batteries and smaller range.
That's a brilliant question. I also was scratching my head about this because, there are different papers showing that in some cases battery emissions could be a bit lower, some higher. The data sources are not fully consistent, but it could be that there are significant emissions related to batteries. But I think to have batteries constructed in countries where the energy mix is again a low carbon intense energy mix, that also helps. And then my personal pick would be the larger and larger battery size is really not doing good for the total energy, total CO2 emissions. And in a couple of cases, even for gas dependent countries, it could flip it that the ICE vehicles are having less total emissions at that point in time. So I'm not so happy with this. I think it would be nice if we had a more integrated way of transport where you shift to different means of transportation. And for the 90% of the cases where you travel less than 100 kilometers, there's no big deal. It might call for some more integrated and smarter solutions.
Okay. Right. If there are no questions, well, we have a session on questions in the reminder of the today's session. So if you all agree, I would move to our next presenter and next presentation. I'm glad that Sabine finally joined us. So yeah, our next presenter is Sabine Preuss. I hope I'm pronouncing it correctly. And Sabine studied psychology at the University Koblenz-Landau and completed the dual master program, International Cognitive Visualization, in Germany, France, and the US. And since 2015, she has been associate researcher and lecturer at the University Koblenz-Landau. 2018, she collected research experience in EU projects done by the Research and Data Unit of European Union Fundamental Rights Agency. Since 2019, she has been a senior scientist at the Fraunhofer Institute for Systems and Innovation Research Competence Center, Energy Technologies and Energy Systems. And in 2020, she completed her PhD on interventions for attitude change towards social minorities. Today, she will be talking about different factors influencing the decision on whether to opt for battery electric or hydrogen vehicles. And Sabine, the floor is yours.
Thank you. I hope you can hear and see my screen and hear me well.
I can,
Perfect.
yeah.
Great. So yeah, thank you for the nice introduction. Together with my colleague Aline, also from Fraunhofer ISI, we conducted 2 studies in Germany regarding the role of knowledge on the adoption of battery electric and hydrogen vehicles, and whether I know it, I like it, I buy it is true, or whether there are other factors that are more important. So the main question is really whether knowledge is the key or whether knowledge has an impact or not. Okay, let's see. Yeah, now it works. So if we take a look at the EU-wide greenhouse gas emissions, we see that the transport sector is the 3rd largest emitter with almost 25%. So of course, to reduce CO2 emissions, it would be best to use bikes or to take the train or even walk. But for sure, there will be cars. Cars will continue to play an important role in the transport system also in the upcoming years. However, there are alternatives, as you all may know, and especially after the last talk, you probably are aware of the different types that we have, but we definitely need those electric vehicles for the energy transition and for a sustainable future. So this talk will especially focus on these three types of electric vehicles. So there are plug-in hybrids, which can be driven electrically or with conventional fuel like diesel. Then there are battery electric vehicles, which are completely battery electric. And the last one, which is especially important for our second study, are hydrogen vehicles, which are also electric vehicles, but are powered by hydrogen. So they have the advantage that there are no long charging times. So there are promising options to tackle climate change and reduce emission in the transport sector. But if we look at the sales share in the EU, we see that for electric vehicles, so battery electric and plug-in are often summarized as electric vehicles. So worldwide, the sales share is still below 5%. So there is a steep increase from 2019 to 2020, but still it's really, really low. So we are far away from our goals. And of course, we need to find ways how to improve this adoption intention or the adoption of battery electric vehicles. And there are many variables that impact adoption intention, for instance, different policies and subsidies, public funding. Also, the context plays an important role. There's research that the income and different social demographic variables have an impact. And there are also individual variables, for instance, the perceived usefulness of electric vehicles. And one of those individual variables may also be knowledge. So knowledge is the most important variable in this talk. And as I said, it is an individual variable, for instance, such as perceived usefulness. And one theory that covers some individual variables pretty well is the diffusion of innovation theory by Rogers. For instance, it was found that compatibility in the theory has an impact, but also triability, which is closely connected to knowledge. So the question that raises is, how exactly do we define knowledge? Because there are many different definitions and different types of knowledge. For instance, Zacharvis stated or made this common differentiation that knowledge between the knowledge of the existence of an innovation and the knowledge of how to use the innovation. However, we will use the definition from Rogers, who states that someone gains knowledge when they learn of an innovation's existence and gain some basic understanding of its function. So we differentiated from experience. So it's really about the existence and the basic functions. And there is also the common differentiation between subjective and objective knowledge, which more or less only differentiates between how you measure it. So the first one, subjective knowledge, is measured with self-report items, and the last one, objective knowledge, is measured with quizzes or tests. So those are the important parts. We know how to define knowledge. Now the question is, does it have an impact on adoption attention? And there are two opposing views. So one says, well, if people only knew better, of course they would adopt electric vehicles. So the opinion that knowledge definitely impacts behavior, and there's research that backs this up. For instance, especially on adoption of electric vehicles, there was a research by Wang and colleagues who found that the lack of knowledge is a psychological barrier for the adoption and also the acceptance of electric vehicles. This position on the left is also supported by the theory of the diffusion of innovation theory, which states for the process of the innovation adaptation at the individual level, Rogers defines a clear path of 3 phases. In the first phase, in the knowledge phase, he says that people collect and gain knowledge about the innovation, and then they form a positive or negative attitude towards the innovation, which is the persuasion phase. And in the third phase, the decision phase, they adopt or reject the innovation. So this can more or less represent the typically and known knowledge, attitude, behavior process. But as I said, this is one perspective, and it's quite intuitive and fits to the results of Wang and colleagues. On the other side, I think all of us know that there might be a knowledge behavior gap, which is also supported by research. For instance, Whitmarsh and colleagues found that climate change researchers fly even more frequently than other researchers. And I think all of us also know the typical example that, of course, you know that you should do more sports or that you should eat healthy, but you don't do it. So maybe it doesn't help if people only knew better. So that's more or less the big question. And there is some research that said, well, there is only this knowledge behavior gap because there are more important mediating variables in between that need to be considered, for instance, attitudes, which fits to the process on the left-hand side. However, there's also this well-known attitude behavior gap. So it's really questions whether knowledge has an impact on behavior and adoption attention or not. And this is the overall question. So we try to replicate the results from Wang and colleagues, but we also try to extend them and really consider the attitudes towards plug-in electric and hydrogen vehicles. So in the first study, this was more or less our assumption, our model. Is there an impact on adoption attention for electric vehicles? So in this first study, we only looked at battery electric vehicles and plug-in hybrids together. And of course, going back to knowledge, we looked whether there is a difference in the different types of knowledge, so between subjective and objective knowledge. What did we do in this first study? We conducted a study with 1,147 participants, and they were all employees at a research association, so they were more male, unfortunately, rather higher educated, and the age was quite evenly distributed. However, there were no people who were retired because they were all employees. And then we asked them for their adoption intention, their attitude towards electric vehicles, as well as their subjective and objective knowledge. The first one measured with 4 items that they answered themselves, and the second one just with a little quiz of 12 questions. And what did we find? We really found a direct effect of objective knowledge on adoption attention, which supports our hypothesis. And also we found the indirect effects. So there is not only the direct effect, but also knowledge has an impact on attitude, and attitude has an impact on adoption attention. So the higher the objective knowledge, the higher your attitude towards the electric vehicle and the higher your adoption attention. This is the result for objective knowledge. For subjective knowledge, we also found a direct effect, which is great and even a little larger than the one on objective knowledge. And we also found the indirect effect. So again, if subjective knowledge is high, your attitude towards the electric vehicle is higher. And if your attitude is higher, your adoption attention is higher as well. So if we compare those results, here you see them just on top of each other, you see that subjective knowledge has a slightly larger impact on adoption attention than the objective knowledge. And what's also interesting is that attitude has an even stronger impact on adoption attention than knowledge, if you compare the direct paths from attitude to adoption attention and from knowledge to adoption attention. However, you have to take those results, you have to interpret them carefully, because they cannot really be compared, and there are not the standardized coefficients here. If you want to know those, just take a look into the paper. I didn't want to overload the slide with too many statistical numbers. So to summarize study 1, we found that knowledge has a direct and indirect effect on adoption attention for battery electric and plug-in vehicles. And this applies for subjective and objective knowledge. And what we could have done better is that the sample was not representative, as you may have noticed, as well as the measures were not ideal, because the order of the measures was not as it is in the model that we tested, and it was also the adoption attention was also a quasi-metric variable. So yeah, there is a need to replicate the results. And of course, we wanted to know whether it only applies for electric vehicles, so battery electric and plug-in hybrid vehicles, or whether it also applies for other technological innovations. So if we take a look on hydrogen vehicles and their share again, so you see it's this tiny little bar on the very top. So the blue one is battery electric, the green one is plug-in hybrids, and then the tiny one at the top is hydrogen vehicles. In Germany, the number is even way smaller, so there are only a few single hybrid vehicles currently on the market. So you see that they're at very different diffusion stage if you compare hydrogen vehicles with battery electric vehicles. So we were wondering, well, probably the knowledge is lower for hydrogen electric vehicles, but maybe the adoption attention is higher, because especially here in Germany, the image and the attitude may be better, because it's not that known yet. So we tested the same model and showed or looked at the differences between plug-in hybrids, battery electric, and hydrogen vehicles, because there are in different diffusion stages. That was the question here, whether we can transfer to hydrogen electric vehicles. And what did we do again? We had this almost same size of people, 1,344 from the general population, and it was this time representative for population in urban spaces. So regarding gender, age, education, and also the regional distribution in Germany. The mean age was about 51. And here, this time, we also adjusted the order of the different measures, and we replaced the measure of adoption attention to make it more methodologically sound. What we found, we replicated the results. So again, there is a direct and an indirect effect from knowledge on adoption attention. And this is true for all three types. So it's not only true for battery electric vehicles and plug-in hybrids, but also for hydrogen vehicles. As you can see, the numbers are comparable, but for hydrogen vehicles, the coefficients are a little higher even. Which is surprising, I think. And it is also important to note that the descriptive statistics really significantly differed between the three electric vehicles. So to sum up, in the second study, we found again the direct and indirect effect for the different types of technologies in the different diffusion stages. So this replicates the results also from earlier research, but also our research, and extends it a little bit because now we know that it can be transferred, and that it also applies in study 1 for subjective and objective knowledge. What we could have changed is, well, there are no hydrogen vehicles yet available or only partly available, so it's all a little hypothetical, and also we measured the adoption attention and not the real adoption. And of course, we only considered one mediator because we only looked at attitudes. And if you think back at the beginning, at the theory, they said, well, whether maybe we should consider several variables as mediators. So maybe it could be helpful to consider additional mediators in our model as well. So, but if we want to answer the overall questions, the overall question, does knowledge really impact adoption attention or not? We can say, yes, it does. But what can be looked at in the future is whether adoption intention can also be impacted for other technical innovations, and whether attitude and knowledge play an important role here. And also the role of hype cycles and the media. So is it important to really have this knowledge transfer for different vehicles and different types of vehicles? And that should be tested in the future. So as a final conclusion, to accelerate the diffusion of sustainable cars, we we don't need to consider the diffusion states, but we should definitely consider knowledge. And we recommend to achieve subjective as well as objective knowledge, as well as creating a positive attitude, because all three of them had a significant impact on the adoption of electric vehicles and the different types of them. That's it. I'm just saying thank you, and I'm happy to answer questions, and I hope I can answer them.
Thank you, Sabine. Currently, we don't have any questions from the audience. Just one remark from Irving Cornelius. He suggests you to connect with Professor Van Steenkist, I hope I'm again pronouncing it correctly, from the University of Ghent in Belgium. And according to Irving, he gave a presentation last Friday discussing the motivation of the public to take part in the energy transition. He concluded that knowledge was also a key enabler. So would you like to comment on that and share your views, perhaps?
Yeah, thank you for this remark. I will try to get in touch with him. It sounds really interesting. As I said, there is a lot of knowledge stating that there is a lot of research stating that knowledge has an impact for adoption attention, and also for different behaviors that are sustainable. So I agree with his view, and I mean the data, the empirical research data also supports it. Exactly.
Thank you. A question from Torsten. Torsten, feel free to shoot the question here live, but this one I'll read it out. Torsten is wondering if the case for hydrogen vehicles is much more dependent on the availability of hydrogen charging and cost / brands of the vehicles and knowledge. And knowledge is a second order effect and difficult to quantify owing to the low numbers of hydrogen cars available. Would you agree to that?
Mm-hmm. Well, yeah, that's a common discussion whether the infrastructure is more important than the knowledge. But I think our research shows that right now there are no hydrogen vehicles and there is no infrastructure for them, and still knowledge has an impact. So I think both of those variables should be considered. It's not only the infrastructure, because that's, for instance, important for compatibility, which is an important variable in the diffusion of innovation theory, but also knowledge is important. So those individual variables are very important. And I think it should, as I said, both should be considered, the infrastructure as well as the knowledge.
Mm-hmm. Okay. I mean, we do have more questions, and we are a bit running out of time. But if you will allow me one question, I might have got it wrong, but if I'm correct, your research has focused on private use rather than on commercial use, right? So what about commercial use? Because I mean, commercial businesses would be more driven on the cost effects, a cost side of the whole deal rather than on knowledge. Of course, implications are also some kind of knowledge, but you know where I'm getting with this. Yeah,
definitely. I think it's completely different if you don't look at the individual, but rather at the bigger players, because I think there are other factors at play, and not, as you said, knowledge is one of them, but probably not the main one. I think here as well, probably policies, funding opportunities play a bigger role here. And I think here is also the infrastructure, because if you cannot really use them, it doesn't make sense to adopt them. But I think knowledge should always be considered, because research shows that it is important.
Yeah. Okay. Thank you for now. I mean, we do have 2 more questions, but we better get going, and we'll leave these questions for later after we finish off the remaining 2 presentations. So once again, thank you, Sabine. And let's move on to our next presenter and his presentation. So this is going to be Stefan Link, who is a researcher and a PhD candidate from Fraunhofer Institute for Systems and Innovations and at the Competence Center Energy Technologies and Energy Systems. Stefan focuses on lithium-ion batteries and alternative powertrains, and he's also an entrepreneur at the Camdideos UG, the institute spin-off aimed at accelerating decarbonization of road freight transport. Stefan is going to be talking about alternatives for heavy-duty vehicles in Germany and in India, and I look forward to hear what Stefan has got to say today. Stefan, the floor is yours.
Hello, and welcome to our presentation. Today, my colleague Daniel Spade and myself, Stefan Link, will give you some insights into our latest research project about fuel cells and hydrogen internal combustion engines to decarbonize road freight transport by heavy-duty vehicles. As showcases, and as global warming potential and environmental protection should concern everything and everybody in the world, we will consider Germany as representative for a highly industrialized country and India as an emerging and fast-growing market. The agenda for today: I will first tell you something about our motivation, then subsequently about the methodology and the data we've used. Then I will hand over to my colleague Daniel Spade, who will tell you something about our economic calculations for Germany and India. And then eventually I will conclude on the presentation today. So about our motivation. On the left side, you see the CO2 emissions by origin or producer respectively. As you can see, transport is responsible for between 13 and nearly 1/5 of total CO2 emissions in India or in Germany, whereas a huge share of these are emitted by heavy-duty vehicles, whereas on the other side, they only account for minor shares in the total vehicle stock. In Germany, only about 10%. What's aggravating the situation is indicated in the middle. Road freight transport steadily and continuously increases. This is indicated by the CAGR, which is basically kind of the average annual growth rate. And for Germany, gives us in the time span from 2000 to 2015, 2% per year, and for India, even 7%. To decarbonize road freight transport, 2 technological pathways exist, as indicated here, whereas today we focus on the second path, which is basically the indirect use via synthetic energy carrier. Here, we especially focus on hydrogen-powered vehicles, which is either fuel cell or potentially a hydrogen combustion engine. About our methodology. Our approach follows 6 major process steps. We first start with the data collection. Then we have the statistical evaluation of these data. We adopted a meta-analysis and learning rate approach. Then following that, we had a main part, which is basically the techno-economic calculations. Subsequently, we validated these with related other studies or expert interviews, whereas we had experts from big OEMs, shippers, and carriers. This eventually leads to these economic results, which, as an outlook, I will send you at the end of the presentation, would ultimately lead to a market diffusion based on these costs. Our approach follows the methodology introduced by Gnan in 2017, where we had especially these 4 topics or parameters, which is annual vehicle mileage, energy prices, tolls, and taxes, specific for each market to ensure transferability from Germany to India and vice versa. Our calculation is indicated on the left-hand side. It's basically a TCO, which is total cost of ownership calculation, which comprises all costs from vehicle acquisition to its operation, like energy costs, tolls, taxes, and all these, and also the resale of the vehicle at the end of the service life. We adopted a net present value approach, which is basically the reason why we have the annual rate, tax rate here. And we adopted full cost accounting. The parameters are indicated here, and all the formulas are explained in the backup. As a scenario, we had a 40-ton tractor-trailer combination with a European configuration and a 1,000-kilometer range. We compared the 2 technologies, fuel cell EV and hydrogen ICE, versus diesel as a reference, and we did this for 3 different time steps, which means that we had a vehicle acquisition in 2020, in 2030, and in 2050. So now let's come to our meta-analysis, which basically summarizes hundreds of different data points from other studies, expert interviews, and different sources. On the left-hand side, you see the meta-analysis for fuel cell system costs. On the right-hand side, for the hydrogen storage type 3, type 4, which is basically highly compressed, yet gaseous hydrogen. You see the big spread here, which basically means that you have high uncertainty here. This is apparent, which is also the reason why we did such an analysis and have not simply pulled out any single data point of any study to especially account for this uncertainty. Eventually, we adopted with a regression, our final cost projections, and the quality of these fits are indicated with the R2 value on the top right corners here. The blue box here indicate the box plots, which is basically the lower and upper quantile. And here you see the min and the max value, which basically visualizes this high spread and this high uncertainty for these 2 main components. Now let's come to the hydrogen ICE engine, which might be a possible enhancement for current diesel engines, because it's a concept based on conventional diesel engines where you have to adjust major systems like the ignition system, the fuel system, engine control. You have to adjust the combustion process, but it's basically the same engine. And ultimately, you can reach a higher efficiency. You have no CO2 emissions and only low NOx emissions. And what's a charming option, you can adapt it very easily to existing engine production, and it's more durable than, in comparison, a fuel cell system. What's the shortcoming today is that today there's no real cost assessment available, which is why we've chosen a learning rate approach and used the similarity between the diesel engine and the hydrogen engine and determined the parameters from current EU6 diesel engines, yet scaled it to a low volume hydrogen ICE production. On the right-hand side, you see our technical analysis and technical assessment based on individual component efficiency here, and then on the left side here, the total powertrain efficiency, which is the lowest for diesel and highest for the fuel cell EV. And as indicated here, you see that the hydrogen ICE has a higher efficiency than diesel engine. To conclude this chapter, I will give you a short hint about our bottom-up cost calculation. On the left-hand side, you see the bottom-up cost calculation for the vehicle, where we consider major powertrain-specific parts and a common vehicle body for all 3 options. And then indicated here in the showcase, the diesel, where you have a transmission, a fuel tank, engine, and the emission after treatment, which basically sums up to the total vehicle price. On the right side, you see the same for diesel and hydrogen biases, where the diesel price is based on the crude oil price, or in the case of synthetic diesel indicated in green, on 100% synthetic PT diesel or power to X diesel. And the right bar here, or the right scale, is for the hydrogen, which is basically here in the dashed lines. And the left side here is for the diesel. What you see is that we have a price decrease for the synthetic fuel, and we have a price increase for the conventional fuel, which basically builds, as I already explained, on from the crude oil price, and then we added taxes, fees, operating margins, transport costs, and all these to derive the final cost. What's important to note here that we assume a 100% zero emission transport, which is basically why that finally we have 100% synthetic diesel in 2050, yet we have neglected the influence of potential biogenic land. Given these background data and information, I will now hand over to my colleague Daniel Speth, who will introduce you our results.
Okay, thank you. Let's start with the results for Germany. On the left-hand side, you can see the total cost of ownership for H2ICE and fuel cell electric vehicles today, in 2030 and in 2050. The diesel vehicle serves as a reference. As you can see, neither the H2ICE nor the fuel cell electric vehicle is cost competitive today or in 2030, assuming average mileage of 120,000 kilometers per year. There are two reasons for this. First, the purchase price for H2ICE and fuel cell electric vehicle will be higher than for diesel vehicle, even in the long term. Second, the energy costs for hydrogen, especially synthetic hydrogen, are quite high today, even though we considered the price cap in Germany. However, sensitivities show that the fuel cell electric vehicle could be cost competitive in 2030 when driving high mileage due to comparatively high energy efficiency. In the long-term perspective, 2050, both hydrogen vehicles will be cost competitive compared to the diesel vehicle. Higher efficiencies and lower fuel prices makes this possible. They benefit from the possibility of making synthetic hydrogen available at a lower price than synthetic diesel. The fuel cell electric vehicle will come close to the TCO of today's diesel vehicle, even though we assume the comparatively high hydrogen price approximately above 7 euros per kilogram. Finally, from a cost perspective, the H2ICE is not competitive to the fuel cell electric vehicle under similar conditions due to its lower efficiency and a bigger hydrogen storage as a cost factor. However, if the range can be reduced, the H2ICE could be economically feasible. Additional aspects, like robustness, for example, for construction vehicles, could be an argument in favor of the H2ICE. To sum this up, in the long term, hydrogen vehicles are competitive in Germany. From an economic perspective, the fuel cell electric vehicle is more attractive than the H2ICE. Now you can see the same figures for India. The general trend corresponds to the development in Germany. Neither the H2ICE nor the fuel cell electric vehicle will be cost competitive to the diesel until 2030. In the long-term perspective, however, they will be the better solution in India too. Due to lower vehicle mileage, approximately 75,000 kilometers per year, the total TCO per vehicle is lower. This is supported by low energy prices. The higher influence of the purchase price is a disadvantage for the more expensive hydrogen vehicles. However, the H2ICE with a comparatively cheap drivetrain could profit if the vehicle range and with the range the tank volume could be reduced. But in general, the overall assessment is quite similar to Germany. Finally, I'd like to share some sensitivity calculations with you. I will present the results for Germany. However, the results for India are somehow similar and we added them to the paper. On the left-hand side, we will write the annual mileage, the fuel price, and the vehicle purchase price by plus minus 20%. Typically, the TCO of commercial vehicles is strongly influenced by operating costs. As you can see here too, the annual mileage has got the highest influence, followed by the fuel price. The effect is even stronger for fuel cell electric vehicles in the lower figure due to the higher efficiency. For example, a 20% fuel price reduction reduces the TCO of the fuel cell electric vehicle by 10% and makes the vehicle cost competitive to the diesel. On the right-hand side, we calculated the necessary price reduction for the H2ICE to become cost competitive with the fuel cell electric vehicle. It amounts to approximately 38% or more or less 50,000 euro. This is roughly equivalent to the cost of the hydrogen tank in 2030. So all in all, the fuel price and the annual mileage are the most important factors to make hydrogen vehicles economically feasible. To make the H2 ICE competitive with the fuel cell electric vehicle, massive purchase price reductions are additionally needed. So far, our main findings, and now Steffen will go on.
Thank you, Daniel. Let's conclude the presentation for today. What we find is that the fuel cell electric vehicle outperforms any hydrogen ICE and outweighs potential higher acquisition costs due to its higher reachable operating efficiency and its potentially lower mass market production costs. What we also find, and what's very substantial, is that the costs for hydrogen storage are more, in some cases, are higher than the rest of the total powertrain, especially for the considered Type 3, Type 4 tanks here. So basically, as Daniel already indicated, there might be a technological change as introduced by Daimler to use liquefied hydrogen, or simply reduce the operating range from 1,000 kilometers to, let's say, 600 kilometers with one full tank. What we also see is, and that's already indicated by Daniel too, is that the hydrogen ICE might be an interesting gap technology because it increases the rentability of potential hydrogen refueling stations, accelerate and prepare the market diffusion of potential fuel cell electric vehicles. And because it's more durable technology, especially for applications where the fuel cell might not be suitable because there are problems with clean air, shocks and vibration, like for example in the construction industry, the H2 ICE engine might be a promising technology. What we see on the left side of some current limitations here, the prime limitation is here that the learning rate approach is the rather easy and simple assessment, which is basically a good first draft, but more detailed consideration would be necessary in the future. And especially here, apart from the 1,000 kilometer operating range, what we assumed is especially that we did not consider the energy system in deep, which basically comprises the whole infrastructure process, but also the large scale synthetic hydrogen production, where we assume it to be possible and to generate the amount of hydrogen needed. And as indicated here in the outlook for market diffusion in Germany, you see the three technologies, which is basically diesel, H2 ICE, and fuel cell with a potential cost-based market diffusion. And what's apparently missing is battery electric vehicles are not included in our research up to date. To wrap up, please find our contact information here. Please feel free to reach out at any time. Then the only thing left for me to say is thank you very much for your attention. And here you can find our references. Thank you very much.
Thank you. I owe everybody an apology here before we continue, because I promised that I would introduce Daniel, but let him introduce himself. So my apology, and I'll combine that with my question. So I'll kindly ask Daniel to introduce himself before we continue, and also if he could carry on by answering my question. Well, what about battery electric vehicles and in-motion charging as a way to enable battery electric vehicles for heavy-duty purposes? How do you find that option to be comparable to what you're offering here?
Well, first of all, thank you for the introduction. No problem at all. As you said, my name is Daniel. I'm a researcher and PhD student at Fraunhofer IC in Germany too, and I'm there for almost 2.5 years. Yeah, quite a good question. I think, especially in dense populated areas or quite dense street areas, for example, in Germany, the battery electric vehicle can gain some profits due to the higher efficiency of the engine. So the total costs are lower even if we think about quite big batteries like 400 or 500 kilometers. Of course, the question is whether the customers will accept lower ranges for battery electric vehicles, since 800 or 1000 kilometers, as we know it today from the diesel vehicle, might not be possible, in my opinion, at least within the next years. But in general, the battery electric vehicles are typically a little bit more cost efficient than the hydrogen vehicles. So from a first point of view, as mentioned before, we didn't include them in this study, but we did some other calculations including them. Yes.
Okay, thank you. Neil, would you like to maybe combine the question from the previous, well, following up the previous presentation from Irving Cornelius, because could be related?
Yeah, sure. Irving says that quite some environmental NGOs are opposed to fuel cell electric vehicles. To what extent do you think they can influence people's choices? I mean, this is possibly a question for Sabine on the behavioral side as well, but you might have a view.
Yeah, I think what's the positive aspect about fuel cell vehicles is that you don't face any range limitations, as it is currently known for the battery electric vehicles. So I think there's a rather positive view on this technology, is typically originating from that. But I think from the social aspect, I think Sabine has to commit their standpoint. Maybe we can pick that question up later in the total Q&A session.
Sure. Can I just ask one technical question before we move on, Dražen?
Sure.
Yeah, of course, Jan.
It's really about your calculations are sensitive to the cost of hydrogen. And as I understand it, the synthetic hydrogen will be produced through electrolysis from renewable energy. Is that correct?
Exactly.
And I guess the cost will be very sensitive to the speed of introduction of renewables, which will enable, cheap peak electricity when the wind's blowing and the sun's shining. So I guess that will be a key factor in, determining the costs of this route.
Absolutely. So that would also be one promising potential for rather the battery electric vehicle, because they would benefit from a rather short-term availability. And for the hydrogen, you have the infrastructure lacking. So you would definitely need a accompanying infrastructure with refueling stations, and you would definitely have to build up the whole energy system to especially supply the amount of hydrogen needed. And there are a few studies available on the total efficiency chain from basically the electricity to basically the supply at the station. And then when you see the efficiency for hydrolysis, for the hydrogen production, and for supplying the raw electricity, you have about 70% for the battery electric vehicle when you have 100% renewable energy at the beginning, and it's rather between 30 to 40% for the hydrogen. So in case the market diffusion or ramp up process, when there's only few green electricity available, that would definitely benefit the battery electric vehicle.
Thank you.
Okay, last but not least, our fourth presenter. Let's move on to our fourth presenter today. This is Sebastian Leopoldus, who is a PhD student at the University of Stuttgart. He received his BSc and MSc in Process Engineering from the Karlsruhe Institute of Technology, and today he's going to be talking about a very, very, as far as I'm concerned, an interesting subject of cooling technologies in transport logistics, and how they contribute to all kinds of emission effects. So Sebastian, the floor is yours.
Dear listeners, Welcome to my presentation with the title Comparison of Cooling Technologies for Transport Logistics. First of all, I would like to say a few words about my motivation. Why is it necessary to deal with this topic in the first place? Here you can see the final energy consumption in freight transport in Germany. After some ups and downs, it has constantly risen in recent years. If you look at the payload distance of the road freight transport by type of goods in the EU, you will see that the goods group food products, beverages and tobacco is in the first place ahead of all other goods groups. Moreover, about 1/3 of all food products transported require either cooling or refrigeration. Today's standard technology for refrigeration on trucks is the vapor compression refrigeration, abbreviated as VCR. About 90% of these VCRs are operated via a dedicated diesel engine, which produces relatively high greenhouse gas emissions. To achieve the energy and climate targets of the EU, further research on alternative cooling technologies is needed. In the following, I would like to present the alternative refrigeration technologies that I used for my comparison. The eutectic system consists of an on-vehicle phase change thermal storage unit, the PCTSU, which contains the phase change material, PCM, and an off-vehicle refrigeration unit, which is powered by electricity. The refrigeration unit charges the system, causing the PCM to change its phase from liquid to solid. When the truck is in operation, the PCM will change from solid to liquid, releasing a cooling effect and discharging the system. The cryogenic cooling is achieved by the evaporation of cryogenic liquids, which are pumped from a tank to the sprayer unit that releases the liquids directly into the refrigerated space. As cryogenic liquids, I considered liquid CO2 and liquid nitrogen. The next system is a vapor absorption refrigeration system that is marked in yellow, coupled with a solid oxide fuel cell, which is marked in red. The vapor absorption system is similar to the VCR, but the mechanical compressor is replaced by a thermal compressor, which you can see in green. The thermal compression is carried out through a mechanism of absorption and desorption. The required heat in the desorber is provided by the fuel cell. The last system is the conventional VCR system, but the compressor is powered by electricity generated in PV cells that are mounted on the roof of the truck instead of an auxiliary diesel engine. Now I would like to explain to you how the required cooling load is calculated. For the calculation of the cooling load, 3 different heat sources are taken into account. First, the transmission heat load. It describes the amount of energy that penetrates the refrigerated space according to Fourier's law. It is a function of the surface area of the truck, the temperature difference between the ambient and the refrigeration temperature, and the thermal transmittance of the truck. Second, the service heat load. You can see the green arrows located at the back of the truck. It describes the energy intake caused by door openings. It is a function of the internal volume not occupied by cargo, the enthalpy change, and the time between door openings. And third, the solar load. This is the amount of heat penetrating the refrigerated space due to solar insolation. I assume that the roof of the truck and one of the sidewalls are always exposed to the sun. Other relevant parameters are the surface absorptivity of the truck and the solar radiation, where I use monthly averages that depend on the latitude. Next, I would like to present the scenarios that were studied. I have considered two scenarios for a long-distance delivery characterized by a high average load, long times between door openings, and the long duration of door openings, and two short-distance deliveries with a low average load, short times between door openings, and short durations of door openings. For both cases, a temperature of 0 degrees and minus 20 degrees Celsius is assumed, resulting in 4 scenarios. In addition, 2 different latitudes are considered: Hamburg in the north of Germany and Catania in the south of Italy, which results in 8 scenarios overall. Now I will explain to you what you can expect from the results. For the environmental comparison, I considered the greenhouse gas emissions. They are divided into operational emissions, meaning the CO2 emissions related to the combustion of fuel and loss of refrigerant, and the production emissions. These are the emissions for the production of the working fluids. Emissions related to the production of the required hardware are not considered. For the economical comparison, I considered the net present value. The costs are divided into investment costs and operational costs, like costs for fuel or electricity. Moving on to the results. We can see that the average monthly cooling loads in scenario 1 and 3, the scenarios with the lower refrigeration temperature, are higher than scenario 2 and 4, which is not very surprising. We can see that the required cooling load in Catania is generally higher than in Hamburg, which is also not surprising given the fact that Catania is closer to the equator. And we can see that the cooling loads for the scenarios with the refrigeration temperature of 0 degrees Celsius do not differ significantly between long and short distance deliveries. Here you can see the composition of the cooling load in December. We can see that the long distance deliveries, scenario 1 and 2, are dominated by the transmission and solar heat load, because the truck and therefore the surface in these scenarios is larger. For the short distance deliveries, scenario 3 and 4, the service heat load increases significantly due to the frequent door openings. Regarding the annual greenhouse gas emissions, you can see scenario 1 on top representing the scenario with the highest emissions, and scenario 4 on the bottom representing the scenario with the lowest emissions. Cryogenic fluids do not have operational emissions, but very high production-related emissions, because this technology is very mass-intensive. Both the VCR and the absorption refrigeration system have high operational emissions, because these systems produce CO2 directly through their energy supply via diesel engine or fuel cell. The eutectic and PV system are the most promising in terms of greenhouse gas emissions. Next, I want to talk about potential limits for the PV-driven VCR system. In this table, you can see the coefficient of performance, the COP, that would be necessary to satisfy the cooling load in the respective scenario for a certain month. Just in case someone doesn't know, the COP is an indicator that describes how efficient a refrigeration unit is operating. While the COP can reach values above 4 in stationary applications, it is usually significantly worse in mobile applications, which is due to the vibrations in the vehicle, for example. This is why I assumed that a COP above 2 is difficult to achieve, and a COP above 2.5 cannot be achieved at all in mobile applications. Surprisingly, the systems are performing better in summer than in winter. The significantly higher cooling demand in summer can be satisfied because the energy intake from the PV cells is also significantly higher. It should be noted that other systems are also limited. For example, the eutectic refrigeration is limited by the size of the storage unit. When the truck is stuck in a traffic jam and the system needs to be recharged again, it could happen that the required refrigeration temperature cannot be held. For the economic analysis, I used the net present value. Again, you can see the scenarios 1 and 4. Since only costs but no revenues are considered, the NPVs are negative. This means the closer to zero, the more profitable the system is. The PV system requires the largest investment in the beginning, but is the only system that shows an upward trend due to its low operational costs. As already mentioned, the cryogenic systems are highly mass intensive to satisfy the required cooling load and therefore have high operational costs, which makes them the most expensive system in most scenarios. When interpreting this analysis, it should be noted that the costs of alternative technologies may fall as market penetration increases. Finally, to the conclusion. Cooling with cryogenic liquids is highly mass intensive and therefore causes more greenhouse gas emissions than the VCR system in the studied scenarios. Eutectic cooling systems, as well as the use of PV electricity for an electric VCR system, seem to be the most promising solutions in terms of emissions and cost reduction. But challenges are arising for the PV system from the strongly fluctuating available solar electricity. Thank you very much for your attention. I'm happy to answer your questions if you have any.
Thank you, Sebastian. We are unfortunately gradually running out of time, and we do have a few questions. Maybe to start with Irving Cornelius's question, to what extent can the nuclear phase out delay the introduction of green hydrogen? But I apologize. This is for the question from the previous session. Maybe so, because we are basically, like I said, run out of time. So maybe we can open up the discussion and so I'm inviting all other speakers to jump in and to turn their cameras on, and so that we can start our discussion reminder of the session. So maybe Neil, you would like to take over? Yeah,
sure. We're very happy to pick up that question that Erwin raised. Slightly provocative, actually. I think the question about nuclear power. Erwin's suggesting that, suggests that to what extent can the nuclear phase out delay the introduction of green hydrogen? There is a risk, he says, that without nuclear power plants, it will take a while before there is a surplus of green electricity. I think I'd take issue with him about the assertion that it'll be a while before there's a surplus of green electricity. Currently now we have periodic surpluses of green electricity in the UK. Periodically, we are paid to use electricity because there's too much of it. I mentioned this in a session yesterday, so. I'm sorry, I'm trying to answer the question. I should pass it over to you guys anyway. What do you think about nuclear power and its impacts on hydrogen? Anybody want to pick that up? Any brave people?
Yeah, feel free to turn your mics on so we can kick off our conversation. I guess Neil, you're gonna have to answer that question yourself.
Yeah, I mean, yeah, my view of that is that as nuclear power, as renewable energy increases in quantity, as it is doing throughout Europe, we are going to have very big periodic surpluses of renewable electricity, which will be an opportunity to store it in whatever form, and hydrogen is an obvious solution to that. So I would push back and ask Erwin to if he were able to speak, I'm sure he would try to justify why you know, the absence of nuclear power or continuation of nuclear power might create a problem for hydrogen. I'm skeptical, but you know, maybe somebody else would like to argue on Erwin's behalf. Doesn't look like it. Oh, Daniel.
Well, I think from a German perspective, the question is quite complicated, since in Germany we try to reduce the power from nuclear energy, but I don't know. Did I get the question right? Yes.
Yeah, it's a highly political question as well, I think.
Exactly.
Yeah, so maybe we should move on. Oh, sorry, Thorsten, go ahead.
Just from my perspective, I mean, generating hydrogen for storage would be nice to have some cheaper electricity. So anything which makes electricity cheaper is advantageous. So there might indeed be some issue.
Okay, so I think we have one question that has been left unanswered. One question for Sabine, and it is quite some environmental NGOs are opposed to fuel cell electric vehicles. To what extent can they influence the people choices? So if you would like, we had other speakers commenting on that, and I think that the question was mostly addressed to you. So if you'd like to pick up.
Yeah, I've also answered it in written, but I can.
Sorry,
no worries, no worries. I only mentioned it briefly in the discussion. I think it can really have an impact. So not only NGOs, but I think the communication and media in general can really have an impact on people's perception and also the adoption attention of electric vehicles. I mentioned briefly those hype cycles. I think they are very important, and the research is slowly developing. So I think there is a lot of research to do, and I think it can be really interesting to see how the media and the communication of NGOs and different media impacts the adoption attention.
Okay, if I may, one general question or remark to all of us. I mean, even from today's session, we may well conclude that the focus has been on individual transport and individual needs, and how to influence the individuals to move from conventional ways of commuting and traveling from A to B, rather than on commercial use. At the same time, we have circumstances like what Sebastian has told us in his presentation. There's a great deal of transport and energy emission generated by that transport is general for commercial use. And so how would you comment on that? I mean, every so often we have events like this, and everybody's focusing on how to buy, how to stimulate people to buy new Teslas and other alternative ways of transport, rather than focusing on things like new cooling technologies for freight transport and so forth. Anybody? Feel free to comment.
Maybe I just can connect with my last answer. So I think that, for instance, the increased public discussion does not only have an impact on the personal or individual level, but also on the market in general. So there is a paper that looked at those increased public discussion and also on investments and the subsequent market development. So I think it really can have an impact, not only on the individual level. And of course, it's not only the increased discussion, but also policies. For instance, in Germany, we saw a peak of the shares due to different funding opportunities and subsidies. So I think those are very important instruments.
Okay, thank you. Yeah, well, we have run out of time, but I'll still, I think that we can get away with one more question for Sebastian. To what extent is your research being tested? Are there vehicles being built and tested using the different refrigeration methods you have described? How do you take this work forward?
So in my work, we haven't conducted any experiments, but the work is based on different papers that you can find on the literature, and some of them conducted experiments. For example, there was a paper where they tried to use the PV cells on the roof of the trucks, and they've driven across whole Europe nearly, and to check if to what extent this could work. From my part, I mean, personally, I cannot say anything about the experiments itself because we didn't conduct them. But what I can maybe say is that this was just, I mean, my work was just a first approach to try to compare the different technologies. And there is still a lot of work to do until we finally can say which technology fits best which use case. And there are other steps planned going on in the next month or years where we can make this comparison deeper and more detailed.
Okay, thank you. I guess that we should keep Liz and other technical staff happy and not overshoot too much with the time available. I'll wrap this up and close the session. Thank you for your active participation to all of you, the speakers and the delegates. I hope that some important questions have been raised and answered. And I hope to see you all tomorrow on our last session on transport. Thank you all. Neil, would you like to say a concluding word?
Yeah, sure. Hope to see you tomorrow, but hope to see you before that at the party this afternoon. I think it starts at 6 o'clock your time. Is that right? It's 5 o'clock here in the UK, but we're all going to have avatars at the party, and there's going to be a special announcement, I understand. So if you can come along, it'd be nice to have a more informal chat.
Okay, thank you all. That's all for today, and see you either this afternoon or tomorrow.
Thank you.